All right, let's talk about something that shapes almost every moment of our lives, often without us even noticing. Think about the sound of a vehicle approaching, the vibrant colors you see, the way a stone dropped in a lake creates ripples, or even, the immense power felt during an earthquake. These are all fundamentally linked by one incredible concept, wave motion.
Exactly. Waves are just everywhere. They're carrying energy, information across space, through different substances, and understanding wave physics is absolutely foundational. It's key to comprehending so much of the physical world, from the tiniest atomic interactions right up to the vastness of the cosmos.
Welcome to a deep dive. Today we're taking that deep dive into the fascinating world of waves. We're going to unpack the core physics concepts that govern how waves behave, what they are, how they move, how they interact, and some truly astonishing ways they show up in our world. This is a really fundamental topic, and getting a solid grasp on it is key, especially maybe if you're navigating physics at the AL level, trying to put these pieces together.
Yeah, our mission today is to cut through some of the complexity. We want to give you a clear, connected understanding of waves. We'll provide those essential insights, the things that hopefully make the concepts click and really show you just how relevant this physics is to everything around you.
Okay, I'm ready. Let's unpack this. So, at the most basic level, when a physicist talks about a wave, what exactly are they describing?
Well, at its core, a wave is a disturbance. It's something that propagates or travels through a medium or sometimes even through empty space. And crucially, it transfers energy from one point to another. The really vital distinction here is that the energy travels, but the material of the medium itself. It doesn't travel along with the wave over any significant distance. The particles of the medium, they just oscillate. They vibrate around their fixed equilibrium positions.
Ah, right. So it's like that perfect analogy, everyone uses the stadium wave. The wave of people standing up and sitting down travels all the way around the stadium. But the individual people, they just move up and down in their seats, yeah? They don't run around the track following the wave. The people are the medium, their movement is the oscillation, and the propagating pattern is the wave carrying energy.
Precisely. That's a great way to visualize it. And when we look at what waves need to travel, we can broadly categorize them into two sort of major families.
Okay, the first family,
Mm.
maybe the more intuitive one, that's mechanical waves. These are the waves that absolutely rely on a physical material, a medium to travel through. This medium can be solid, liquid, or gas.
Right. Think about familiar examples. Sound waves moving through the air or water, those ripples you see expanding on a pond surface, or the waves that travel along a guitar string when you pluck it. In all these cases, the energy of the wave is transferred through the vibrations and interactions of the particles that make up that medium. One particle pushes or pulls its neighbor, passing the disturbance along.
Okay, then we have the second, arguably more mysterious family, electromagnetic waves. These are the rebels, aren't they? They do not need a material medium to travel. They can happily zoom right through the vacuum of space.
Yes, exactly. This is the family that includes things like visible light, radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays. Big family. Fundamentally, they're composed of oscillating electric and magnetic fields. These fields generate and sustain each other as they travel. And their defining characteristic, especially when traveling through a vacuum, is their speed. They all travel at the speed of light, which is approximately 3 times 10 to the power of 8 meters per second, just incredibly fast.
Wow. Okay, so we have waves that need stuff to travel through and waves that don't. But within those categories, the stuff itself or the field, they can move in different ways relative to the direction the wave is actually traveling, right? This is where we get into transverse and longitudinal wave motion.
Exactly. Let's start with transverse waves. In a transverse wave, the particles of the medium or the oscillating fields, in the case of electromagnetic waves, they move or vibrate in a direction that is perpendicular, so at a right angle to the direction that the wave itself is propagating.
Right. The best way I picture this is shaking a stretched string. Like if you tie one end and shake the other end up and down, the bumps and dips, the wave will travel horizontally along the string. But you notice how the individual bits of string are only moving vertically, up and down. The wave moves horizontally, the particles move vertically. That 90-degree angle is the key thing.
Perfectly put. And in transverse waves, we identify the points of maximum displacement upwards, let's say, as crests, and the points of maximum displacement downwards as troughs. Visible light is a prime example of a transverse wave. Its electric and magnetic field oscillations happen perpendicular to the light's direction of travel. Surface water waves are also a very visual example. As the wave moves across the surface, the water particles primarily bob up and down. Oh, and seismic S waves, those slower earthquake waves, they're also transverse.
Okay, so perpendicular motion for transverse. Got it. What about the other type?
The other type is longitudinal waves. Now here, the particles of the medium oscillate back and forth, but in a direction that is parallel to the direction the wave is traveling.
The classic illustration here is a slinky, isn't it? If you push one end of a slinky inwards, you create a compressed region. And if you pull it outwards, you create a stretched region, a rarefaction. These regions of compression and rarefaction, they travel along the slinky. The individual coils of the slinky are moving back and forth horizontally, parallel to the horizontal movement of the wave itself.
Exactly. And the most important everyday example of a longitudinal wave is sound traveling through air. When a speaker cone, or maybe a tuning fork, vibrates, it pushes against the air molecules next to it. This creates a region where they're momentarily crowded together. That's a compression. It's a region of higher pressure and density. Then, as it moves back, it leaves a space where the molecules are more spread out. That's a rarefaction, a region of lower pressure and density. These pulses of compression and rarefaction propagate outwards through the air as the sound wave. Seismic P waves, the fastest earthquake waves, they're also longitudinal.
So transverse is perpendicular jiggling, longitudinal is parallel pushing and pull. Okay, makes sense. Now, how do we actually describe or measure these waves quantitatively? What are the key numbers we need?
Okay, we use several fundamental parameters. First, there's amplitude, typically denoted by A. This is the maximum displacement or distance that a particle or a field in the medium moves away from its normal, undisturbed position, its equilibrium point.
And the amplitude tells us something crucial about the energy the wave is carrying, doesn't it? Like how intense it is.
Absolutely. A larger amplitude means the wave is carrying more energy. Think of a bigger ripple on the water or brighter light. Both have larger amplitudes and carry more energy. For sound, a larger amplitude corresponds directly to a louder sound. More energy, more loudness.
Okay. Next up is wavelength, often represented by the Greek letter lambda. What does that measure?
Wavelength is the physical length of one complete wave cycle. For a transverse wave, you can measure it as the distance from the peak of one crest to the peak of the very next crest, or from one trough to the next trough. For a longitudinal wave, it's the distance between, say, the center of one compression and the center of the next compression. Or from one rarefaction to the next, it's essentially the spatial period of the wave, how long one full wave pattern is.
Then we have frequency. This measures how quickly the oscillations are happening, right?
Precisely. Frequency is defined as the number of complete wave cycles or oscillations that pass a specific fixed point in space per unit of time, usually per second. The unit for frequency is hertz, abbreviated hertz. 1 hertz just means 1 cycle per second, so a higher frequency means the wave is oscillating more rapidly.
And related to frequency, there's also the period, T.
Yeah, the period is simply the time it takes for one complete oscillation or one full wave cycle to pass a given point. So it's just the inverse of the frequency. T equals 1 divided by F. If a wave has a frequency of 100 hertz, meaning 100 cycles pass per second, then the time for one cycle to pass is just 1100th of a second.
Makes sense. Finally, we have wave velocity.
Wave velocity is the speed at which the entire wave disturbance, the pattern of crests and troughs or compressions and rarefactions propagates through the medium or space. It's how fast the wave is actually moving from one location to another.
And here I think is where a truly powerful relationship emerges, connecting these three key parameters, velocity, frequency, and wavelength.
Indeed, this is fundamental. For any wave, regardless of its type or the medium it's traveling through, its velocity is equal to the product of its frequency and its wavelength. So V equals F times E. This equation is just essential. If you know any two of these quantities for a wave, you can immediately calculate the third.
It's fascinating how simple that equation looks, yet how universally it applies.
Yeah.
Like you mentioned earlier, if you consider a radio wave transmitting at 200 kilohertz, that's 200,000 hertz, and you measure its wavelength to be 1,500 meters, using VFU gives you 200,000 hertz times 1,500 meters, which works out to 3 times 10 to the 8 meters per second, which is exactly the speed of light. It confirms it's an electromagnetic wave.
Exactly. And the same equation works perfectly for sound, too. If you have a tuning fork vibrating at, say, 256 hertz, a common frequency for middle C, and you measure the wavelength of the sound wave it produces in air to be about 1.36 meters, then the speed of that sound wave is 256 hertz times 1.36 meters, which is approximately 348 meters per second. That's a typical speed for sound in air at room temperature. The equation really connects the properties determined by the source, which sets the frequency, and the properties of the medium, which determines the velocity, and that, in turn, dictates the wavelength.
When we look at simple, regular waves, they often have this characteristic shape, right? Kind of like simple harmonic motion appearing sinusoidal.
Yes, very often. If you plot the displacement of particles in a medium along the direction of travel at a single instant in time, or if you track the displacement of just one single point in the medium over time as a wave passes through it, you'll often see a sine curve or a cosine curve. We can capture this mathematically with equations like y equals a sine of plus or minus kx.
Right, where y is the displacement at position x, and time t, a is the amplitude we just talked about.
Yeah.
And then we have these Greek letters, omega and k.
Correct. O is the angular frequency. It's related to the regular frequency f by O equals 2f. It essentially tells you how quickly the wave's phase, its position in the cycle, is changing with time. And k is the wave number. It's related to the wavelength U by k equals 2. It tells you how quickly the wave's phase is changing with distance. The plus or minus sign between the U and x terms just tells you which direction the wave is traveling along the x-axis. While the full equation might look a bit complex at first glance, it's really just a concise mathematical way of capturing all the wave's key characteristics: its height, a, its rate in time, f or o, and its repeating pattern in space, or k, as it moves.
We also sometimes hear the term wavefront. What's a simple way to think about that?
A wavefront is basically just a surface, or maybe a line in 2D, where all the points on that surface or line are in the same phase of their oscillation. They're all doing the same thing at the same time. Imagine dropping that stone in a still pond again, the expanding circles you see. Those are the wavefronts. Each circle connects points that are, say, at the crest of the wave at that instant. For sound coming from a small source, the wavefronts would be expanding spheres. For light that's traveled a long way from its source, like sunlight, the wavefronts can be approximated as flat planes over small regions.
And the waves we've been talking about so far, the ones that transfer energy from one place to another, these are sometimes specifically called progressive waves, just to distinguish them from other types.
That's right. Progressive waves are the ones that carry that disturbance and energy forward from one location to another. It helps distinguish them from stationary waves, which, as the name suggests, behave differently. We'll definitely get to those.
Okay, that covers the fundamental nature and description of waves pretty well, I think. But things get really interesting when waves encounter boundaries or pass into different materials or even meet other waves, right? How do they behave then?
Yes, this brings us to the fundamental interactions or behaviors of waves. The first one is reflection. This happens when a wave strikes a boundary between two different media and, well, it bounces back into the original medium.
Like light bouncing off a mirror, that's reflection. Or sound bouncing off a wall to create an echo. And for simple cases like plane waves hitting a flat surface, there's a simple rule. The angle at which the wave hits the surface, the angle of incidence, is equal to the angle at which it bounces off the angle of reflection. Measured relative to the normal, of course.
Correct. And crucially, when a wave reflects, its speed and its wavelength don't change because it remains in the same medium. Only its direction of travel changes.
Okay, bouncing back is reflection. What's next?
Next is refraction. This is the phenomenon where a wave changes direction it bends as it passes from one medium into another. And this bending occurs precisely because the wave speed changes as it enters the new material.
And this is where that V-Fu equation becomes really insightful again, isn't it? The frequency of the wave is determined by the source that created it, and that frequency generally doesn't change when the wave moves into a new medium. So if the velocity changes because the medium changes, the wavelength must also change proportionally to keep the equation balanced.
Exactly. It's this change in speed and wavelength that causes the wave to bend or change direction, provided it crosses the boundary at an angle other than straight on, perpendicular. Think about light moving from air into glass or air into water. The speed of light is slower in these denser optical media. So as light enters the glass or water, it slows down, its wavelength decreases, and it bends towards the normal line, that imaginary line perpendicular to the surface. Then, when it exits back into air, it speeds up, its wavelength increases, and it bends away from the normal. Water waves moving from deep to shallow water do exactly the same thing. They slow down, their wavelength shortens, and they bend. The amount of bending is related to how much the speed changes, described mathematically by Snell's law.
Okay, reflection is bouncing, refraction is bending due to speed change. What else?
Then we have diffraction. This is the bending of waves as they pass around the edges of obstacles, or the spreading out of waves after they pass through openings or slits.
Right, the spreading out.
And the key insight with diffraction is that the amount of bending or spreading is most significant when the size of the obstacle or the opening is comparable to, or even smaller than, the wavelength of the wave. If the opening is very wide compared to the wavelength, the wave just passes through pretty much in a straight line, with only minimal spreading at the edges. But if the opening is narrow, comparable to the wavelength, the wave spreads out dramatically on the other side.
This explains why you can easily hear someone talking around a corner even though you can't see them, right? Sound waves have wavelengths ranging from centimeters up to several meters, which are often comparable to the size of doorways or buildings. So sound diffracts significantly around corners.
Exactly. Whereas visible light has incredibly tiny wavelengths, down in the nanometer range. That's vastly smaller than most everyday objects or openings. Because the wavelength is so tiny compared to the obstacle, light diffraction is usually negligible in everyday situations. That's why light tends to cast sharp shadows. It doesn't bend around corners very noticeably unless the opening is extremely small.
Okay. And the final key behavior, the one that governs what happens when waves occupy the same space.
That would be the principle of superposition.
This one sounds simple, but it seems incredibly powerful.
It really is. It simply states that when two or more waves are simultaneously present in the same medium, the total displacement of the medium at any point and at any given time is just the vector sum of the displacements that each individual wave would produce on its own at that same point in time.
So you just add them up. Crests add, troughs add, but if a crest meets a trough.
Then they subtract. You add the individual wave displacements together, taking their direction, positive or negative displacement from equilibrium into account. This simple principle is the absolute foundation for understanding how waves combine and interfere, leading to all sorts of fascinating phenomena like interference patterns and stationary waves.
Which leads us perfectly into what happens when waves collide or combine in these fascinating ways: interference, stationary waves, and beats. Let's start with interference.
Okay. Interference occurs when two or more waves overlap and combine according to that principle of superposition we just mentioned. The result is a new wave pattern. Now, for us to see a stable interference pattern, one that doesn't shift around randomly over time, the waves involved must come from what we call coherent sources.
Coherent sources. What exactly does coherent mean in this context?
Coherent sources are sources that produce waves with the exact same frequency, and they must maintain a constant phase difference between them. Their crests and troughs have a fixed, predictable relationship over time. Lasers are really good examples of coherent light sources. Regular light bulbs, on the other hand, emit light randomly, so they're generally not coherent.
Okay, so assuming we have coherent waves interfering, what kinds of patterns do we actually get?
You get specific regions of constructive interference and regions of destructive interference. Constructive interference happens where the waves meet in phase. This means the crests of one wave align perfectly with the crests of the other, and the troughs align with the troughs. According to the superposition principle, their amplitudes add up. The result is a wave with a larger amplitude. If it's light, it's a brighter spot. If it's sound, it's a louder sound. Reinforcement.
Makes sense. And destructive interference.
Destructive interference occurs where the waves meet out of phase. The simplest case is when they're exactly half a cycle out of phase, meaning the crest of one wave aligns perfectly with the trough of another. In this case, the displacements are in opposite directions, and they tend to cancel each other out. The result is a wave with a smaller amplitude, and if the two interfering waves have the exact same amplitude and are perfectly out of phase, they can completely cancel each other out, resulting in zero displacement, a dark spot for light, or a quiet spot for sound. Cancellation.
You can actually see these patterns quite clearly in things like ripple tanks in the lab, right? With two dippers creating waves in water.
Absolutely. You get those characteristic lines radiating outwards, lines where the waves are big, constructive interference, alternating with lines where the water surface is almost completely calm, destructive interference. It's a beautiful demonstration of superposition.
Now, stationary waves, which you mentioned earlier, sometimes called standing waves, are a particularly important type of interference pattern, aren't they?
Yes, they are very important. Stationary waves are formed when two identical progressive waves traveling in opposite directions superpose in the same medium. This commonly happens when a wave reflects off a boundary like the end of a string, and the reflected wave travels back, interfering with the incoming wave that's still traveling towards the boundary. The key characteristic is that they appear to stand still between certain points. They do not seem to transfer energy progressively along the medium like a traveling wave does.
So if the energy isn't traveling along the wave, what's actually happening to it?
The energy is essentially trapped or localized in segments of the wave. Stationary waves have specific points along them called nodes. These are points of zero displacement that remain fixed in position. They don't move up and down at all. And between the nodes are points of maximum displacement called antinodes. These are where the oscillation is largest. Another interesting feature is that all the particles in the medium between two adjacent nodes oscillate together perfectly in phase. But the segment on one side of a node is always oscillating exactly out of phase, 180 degrees different, with the segment on the other side of that node.
The classic example always used to study this is a stretched string fixed firmly at both ends, like on a guitar or maybe a sonometer in the lab.
Exactly. That's the perfect system to visualize it. Since the ends of the string are fixed, they must always be nodes, points of zero displacement. So the simplest way such a string can vibrate to form a stationary wave is with a node at each end and just a single antinode right in the middle. This is called the fundamental mode of vibration, or sometimes the first harmonic.
And for this fundamental mode, the length of the string L corresponds exactly to half a wavelength, right? The distance from node to node is O2.
Precisely. So the wavelength of the fundamental is U equals 2L, but the string can vibrate in other ways too, more complex patterns that also fit the boundary conditions.
Right. The overtones or higher harmonics.
Yes. The next simplest mode is called the second harmonic, or the first overtone. In this mode, the string vibrates in two segments. It has nodes at the ends and also one node right in the exact middle. So there are two antinodes, one in each half. Here, the total length of the string L is equal to one full wavelength, L equals EO. Or you can write that as EU equals 2.
Okay.
Then the third harmonic, or second overtone, has the string vibrating in three segments. It has nodes at the ends, plus two additional nodes dividing the string into three equal parts, so there are three antinodes. In this case, the length L equals 1.5 wavelengths, L equals 3,2, which means the wavelength for this mode is equals 2L3.
I think I see a pattern emerging here. The wavelengths of the possible stationary waves, these harmonics, seem to be given by un equals 2ln, where n is an integer 1, 2, 3, and so on, representing the harmonic number.
You've got it. That's exactly the relationship.
Yeah.
N tells you how many vibrating segments or antinodes there are. And since we know the speed of a wave traveling on the string, V is determined by the properties of the string itself specifically, its tension T and its mass per unit length m. The formula is V equals square root of T divided by m. We can find the possible frequencies for these stationary waves using our fundamental wave equation, VL phi.
Okay. So for the nth harmonic, the frequency Fn would be V divided by un. So Fn is square Tm 2ln, which rearranges to Fn n 2l times square Tm.
Precisely. And look at that result. The possible frequencies at which stationary waves can form on the string are integer multiples, n1, 2, 3 of the fundamental frequency, F0, which is 12L square Tm. These specific allowed frequencies, F0, 2F0, 3F0, etc., are called the resonant frequencies of the string. If you try to force the string to vibrate by applying an external force, you'll get the largest amplitude response, the biggest stationary wave, if the driving frequency matches one of these resonant frequencies.
That's why touching a guitar string lightly,
Yeah.
exactly at the halfway point while plucking it, produces a note that sounds an octave higher, right? You're forcing a note to form there, which suppresses the fundamental and emphasizes the second harmonic, which has double the frequency.
Exactly. You're selecting a specific mode of vibration. Wind instruments work on a very similar principle, but they involve stationary sound waves set up in columns of air inside pipes. The boundary conditions, whether the ends of the pipe are open or closed, determine where the nodes and antinodes of pressure or displacement can form, and thus determine the resonant frequencies and the notes the instrument can play.
Speaking of sound, there's another fascinating phenomenon that arises from superposition when frequencies are involved.
Beats.
Ah, yes, beats. Beats occur when two sound waves of slightly different frequencies travel in the same direction and overlap, interfering with each other. Because their frequencies are slightly different, the phase difference between them doesn't stay constant. It changes continuously over time.
So does that mean sometimes they'll be in phase, leading to constructive interference, and then a moment later they'll drift out of phase, leading to destructive interference?
That's exactly what happens. This continuous drifting in and out of phase means that the amplitude of the resulting combined wave periodically varies. It goes from a maximum when they are constructively interfering down to a minimum when they are destructively interfering and back up again. And we perceive this periodic variation in the amplitude of the sound wave as a periodic variation in the loudness of the sound. You hear these pulses of loud and quiet sound. That's the beat phenomenon.
And the rate at which these loud pulses occur, that's the beat frequency.
Yes. The beat frequency is defined as the number of times per second the loudness reaches a maximum or a minimum, and it turns out to be equal to the absolute difference between the frequencies of the two original waves. So, beat frequency, B equals A of F. The closer the frequencies, the slower the beats.
This is incredibly useful for tuning musical instruments, isn't it?
Oh, absolutely essential. If you play a standard reference note, say from a tuning fork or an electronic tuner, and you play the corresponding note on the instrument you're trying to tune, if their frequencies aren't perfectly matched, you'll hear those beats, that wah, wah, wah sound. You then adjust the instrument's tuning, like tightening or loosening a string, until the beat frequency decreases and eventually disappears altogether. When you no longer hear any beats, it means the difference in frequencies is zero. They're perfectly in tune.
Very cool. Okay, let's maybe take a slightly closer look at some specific types of waves now, starting with sound, which we've touched upon quite a bit already.
Sure. Sound in air, as we established, is a mechanical longitudinal wave consisting of compressions and rarefactions. But our perception of sound, the way we actually experience it, is usually described by subjective characteristics that are linked to its physical wave properties. These are mainly loudness, pitch, and quality or timbre.
Loudness is probably the most obvious one, how loud something sounds.
Right. Loudness is primarily related to the intensity of the sound wave. Intensity is defined as the power or energy per unit time that the wave carries per unit area. And physically, the intensity of a wave is proportional to the square of the wave's amplitude. So a bigger pressure amplitude in the sound wave means a higher intensity, which we perceive as a louder sound. Because the range of sound intensities the human ear can detect is absolutely enormous, from the faintest audible sound to sounds that cause pain, loudness is often measured on a logarithmic scale called the decibel scale, abbreviated dB. The human hearing range typically extends from around 0 dB, which is defined as the threshold of hearing for a typical young person, up to about 120 dBs or even higher, which is the threshold of pain. Prolonged exposure to sounds above maybe 85 dBs can cause hearing damage.
Okay, loudness is amplitude intensity, and pitch is related to frequency.
Correct. Pitch is our subjective perception of how high or low a sound is, and it's directly related to the fundamental frequency of this sound wave. A higher frequency corresponds to a higher pitch, like a flute or a violin note, and a lower frequency corresponds to a lower pitch, like a tuba or a bass drum. The typical range of frequencies that a young, healthy human ear can hear is roughly from about 20 hertz, 20 cycles per second, at the low end, up to about 20 kilohertz, 20,000 hertz, at the high end. This range tends to decrease, especially at the high frequency end, with age or exposure to loud noise.
What about sounds outside that range? You mentioned them briefly.
Right. Sound waves with frequencies below 20 hertz are called infrasound. We can't hear them, but some animals like elephants can use them for long-distance communication. Very low frequency sounds can also be produced by things like earthquakes or volcanoes. And sound waves with frequencies above 20 kilohertz are called ultrasound. Again, we can't hear them. But animals like bats and dolphins use ultrasound for echolocation, navigating, and finding prey. And ultrasound has found numerous important applications in technology and medicine, as you often see advertised or used. It's used extensively in medical imaging, creating sonograms, because these high-frequency waves can be focused and reflect off internal body structures to produce detailed pictures. Sometimes they even use the Doppler effect with ultrasound to measure blood flow velocity.
Right, I've heard of that.
It's also used in physiotherapy for deep tissue heating, in some dental procedures for cleaning, in industrial testing to detect hidden flaws in materials without damaging them, and apparently even in some chiropractic treatments, although the mechanisms there might be less well understood.
Okay, loudness, pitch.
Mm-hmm.
What about the third characteristic? What gives a sound its unique flavor, its quality or timbre? Why does a piano sound different from a violin even when they play the exact same note at the same loudness?
Timbre. That's what allows us to distinguish between different instruments or different voices. It's related to the complexity of the sound wave's waveform, its actual shape over one cycle. You see, most musical notes and voices don't produce a pure, simple sinusoidal wave corresponding to just the fundamental frequency. Instead, they produce a complex wave that is a combination of the fundamental frequency plus various overtones, which are usually harmonics, integer multiples, of the fundamental frequency. Each instrument or voice produces a unique mix of these overtones with different relative intensities or amplitudes. It's this specific combination and the relative strengths of the fundamental and its overtones that creates the unique shape of the complex waveform. Our ear and brain interpret this complex waveform shape as the sound's characteristic quality or timbre.
So tuning fork sounds quite plain
Because a tuning fork produces a sound that is very close to a pure sine wave, mostly just the fundamental frequency with very weak overtones. That's why its sound is often described as pure, but perhaps less rich or interesting than the sound of a musical instrument, which has a richer harmonic content.
we touched on the speed of sound earlier, too. It's quite fascinating how much it can vary depending on what it's traveling through.
Yes, it varies significantly. The speed of sound depends crucially on the properties of the medium it's traveling through. Specifically, it depends on how stiff or resistant to compression the medium is, which relates to its elasticity or bulk modulus, and also on its density. Generally speaking, sound travels fastest in solids, where the particles are packed closely together and interact strongly, allowing vibrations to pass quickly. It travels slower in liquids and slowest in gases, where particles are much farther apart and interact less strongly. Just to give you some rough numbers, the speed of sound in steel is around 5,000 meters per second. In water, it's about 1,500 meters. And in air, at room temperature, as we calculated earlier, it's roughly 340 meters. So, big differences.
Does temperature matter, too?
Yes, especially for gases. For gases like air, the speed of sound increases with temperature. This is because the gas molecules themselves are moving faster at higher temperatures, so they collide more frequently and can transmit the sound disturbance more quickly. The relationship involves the square root of the absolute temperature.
Okay, let's shift gears now to the other big family, electromagnetic waves, like light. Since they are transverse waves, they exhibit a property that longitudinal waves, like sound, don't have, right? Polarization.
Exactly. Polarization is a property unique to transverse waves. It refers to the phenomenon of restricting the oscillations of the wave to a single plane perpendicular to the direction of propagation. Remember, in a transverse wave, the oscillations can happen in any direction perpendicular to the travel direction. Unpolarized light, like the light coming from a standard incandescent lamp or from the sun, consists of a mixture of waves whose electric fields are oscillating randomly in all possible planes perpendicular to the direction the light is traveling.
So it's vibrating every which way, basically. How do you polarize it, then? How do you restrict that vibration?
You typically pass the unpolarized light through a special type of filter called a polarizing filter, often made of a material like Polaroid. You can imagine it acting like a sort of picket fence or a microscopic set of parallel slits for the light waves. If you send waves down a rope by wiggling it randomly in all directions, only the wiggles that are parallel to the gaps in the fence can pass through. The perpendicular wiggles get blocked. A polarizing filter works similarly for the electric field oscillations of light. It has a specific transmission axis or pass axis, and it only allows the components of the light's electric field oscillations that are parallel to this axis to pass through. The components perpendicular to the axis are absorbed or reflected.
So the light that emerges is vibrating only in one direction.
Precisely. The light that emerges from the filter is then said to be plane polarized, meaning its electric field is oscillating back and forth predominantly in a single plane that contains the transmission axis and the direction of propagation. And you can demonstrate this easily. If you take a second identical polarizing filter, sometimes called an analyzer, and place it in the path of this polarized light, what happens depends on how you orient the second filter. If the transmission axis of the second filter is aligned parallel to the first one, the polarized light passes through relatively unchanged. But if you rotate the second filter so its transmission axis is perpendicular at 90 degrees to the first filter's axis, then it blocks virtually all of the polarized light. Almost no light gets through. This crossed polarizer's demonstration is strong evidence that light is indeed a transverse wave, because longitudinal waves can't be polarized in this way.
And this polarization has some very practical uses in everyday life.
Oh, absolutely. Polarizing sunglasses are a fantastic example. They are designed to reduce glare, particularly glare reflected from horizontal surfaces like water, snow, or wet roads. This works because when light reflects off such surfaces at certain angles, it becomes partially or strongly polarized horizontally. The polarizing filters in the sunglasses have their transmission axis oriented vertically, so they preferentially block this horizontally polarized glare, making it much easier and more comfortable to see.
Right. They really do cut down glare noticeably.
We do. Polarization is also used in photography filters to reduce reflections or darken blue skies. It's fundamental to how liquid crystal displays, LCDs, work. The screens on your phone, computer monitor, or TV use polarizing filters in conjunction with liquid crystals to control whether light passes through each pixel. And some types of 3D movie systems use glasses with polarizing filters oriented differently for each eye to create the illusion of depth.
Okay, now let's talk about another really important wave phenomenon, the Doppler effect. This is something I think almost everyone has experienced directly, even if they don't know the name.
Yes, the Doppler effect is very relatable. It's the apparent change in the frequency and therefore also the wavelength of a wave as observed by a listener or observer when the source of the wave or the observer themselves or both are moving relative to each other or relative to the medium the wave is traveling through.
The absolute classic example is the sound of an ambulance siren or a train horn as it approaches you, passes you, and then moves away. The pitch seems to change.
Precisely. As the ambulance or train approaches, the pitch of the siren sounds distinctly higher than its actual true pitch, the frequency it would have if it were stationary. Then, just as it passes you and starts moving away, the pitch suddenly drops and sounds noticeably lower than its true pitch.
Why does that happen? What's the physics behind that pitch change?
It's all about the relative speed between the source and the observer, and how that affects the rate at which the wavefronts, the crests or compressions, arrive at the observer's location. Think about the approaching source. As it emits wavefronts, it's also moving towards you, essentially chasing the waves it just sent out in your direction. This motion effectively bunches up the wavefronts in front of it. They arrive at your ear closer together in time than if the source were stationary. Since more wavefronts reach your ear per second, you perceive this as a higher frequency, hence a higher pitch. The wavelength you observe is correspondingly shorter.
Okay, so bunching up means higher pitch, and when it moves away.
When the source moves away from you, it's moving away from the wavefronts it's emitting in your direction. This effectively stretches out the distance between successive wavefronts arriving at your ear. They arrive less frequently. Fewer wavefronts reach your ear per second compared to if the source were stationary. You perceive this as a lower frequency, a lower pitch. The observed wavelength is longer. The same logic applies if the source is stationary and you're moving towards or away from it. It's the relative motion that counts.
There's a general formula that lets you calculate this apparent frequency shift, right?
Yeah.
It looks a bit complicated with all the pluses and minuses.
Yes, there's a standard formula, though deriving it requires careful consideration of the relative speeds. The observed frequency, let's call it f prime, is related to the actual source frequency, f0, the speed of the wave in the medium, v, the observer's speed relative to the medium, uo, and the source's speed relative to the medium, us. The formula is generally written as fv, colo, v, uo, vqo. The tricky part is getting the signs right. They depend on the directions of motion. Generally, you use the upper signs, plus in the numerator and the denominator, for motion towards each other, which increases frequency, and the lower signs, in the numerator plus in the denominator, for motion away from each other, which decreases frequency. You have to think carefully about whether the relative speed between observer and wavefronts is increasing or decreasing.
Okay, so the formula captures all those scenarios. While we most often hear this effect with sound, you mentioned it applies to all waves, including light. And this has absolutely incredible implications in astronomy.
Oh, it's fundamentally important. It's one of the most powerful tools astronomers have for understanding the universe's dynamics. Light waves coming from distant stars and galaxies exhibit the Doppler effect due to their motion relative to us here on Earth. If a star or galaxy is moving away from us, the light waves reaching us are stretched out by this motion. This means their observed frequency is shifted towards the lower frequency, longer wavelength end of the electromagnetic spectrum. For visible light, this shift is towards the red end of the spectrum, so we call this phenomenon redshift.
And if it's moving towards us,
then the light waves are bunched up or compressed by the relative motion. The observed frequency is shifted towards the higher frequency, shorter wavelength end of the spectrum, which for visible light is the blue end. We call this blue shift. By carefully measuring the amount of redshift or blue shift in the light spectrum from a celestial object, astronomers can determine the speed at which that object is moving towards or away from us along the line of sight. It's incredibly precise.
and this is how we know the universe is expanding.
It's a key piece of evidence. In the early 20th century, astronomers like Edwin Hubble observed that light from nearly all distant galaxies is redshifted, meaning they are moving away from us. Furthermore, they found that the farther away a galaxy is, the greater its redshift, implying it's receding from us faster. This observation strongly supports the theory that the entire universe is expanding.
That's amazing. And the Doppler effect has more down-to-earth uses, too.
Absolutely. Police radar guns use the Doppler effect. They emit radio waves, or sometimes microwaves, towards a moving vehicle. The waves reflect off the vehicle and return to the radar gun. Because the vehicle is moving, the frequency of the reflected waves is Doppler shifted. By measuring this frequency shift, the gun can calculate the vehicle's speed very accurately. And as we touched on earlier, medical ultrasound often uses the Doppler effect to measure the speed of blood flow in arteries or veins. Ultrasound waves are reflected off the moving red blood cells, and the Doppler shift in the reflected waves reveals how fast the blood is flowing, which can help diagnose circulatory problems.
Okay, but what happens if the source's speed gets really extreme? What if it's equal to, or even greater than, the speed of the wave itself in the medium? Like a jet plane breaking the sound barrier.
Ah, that's when you enter the realm of supersonic speeds and the dramatic phenomenon of shock waves. When an object, like a supersonic jet aircraft, travels through air faster than the speed of sound in that air, which is about Mach 1, it's constantly outrunning the sound waves, compressions it produces. Instead of the wavefronts spreading out nicely in front of it, they can't get out of the way fast enough. They effectively pile up and constructively interfere along a cone-shaped surface that trails behind the object. This cone consists of a region of very highly compressed air. It's a shock wave.
And the sonic boom that we hear on the ground.
The sonic boom is the sound signature associated with the passage of that shock wave. As the conical shock wave sweeps across the ground, an observer experiences a very abrupt and large change in air pressure. First, a rapid increase as the compressed front hits, followed quickly by a rapid decrease back to normal or even below normal pressure. Our ears perceive this sudden pressure change as a loud, sharp, explosive sound, the sonic boom. It's not just a one-time event when the plane breaks the barrier. The shock wave is continuously generated as long as the object travels faster than sound, and the boom is heard by anyone the cone sweeps over. It's a direct and powerful consequence of the source exceeding the wave speed.
Fascinating and loud. Okay, let's bring some of these concepts back together and look at some more dramatic real-world impacts and applications of wave physics. We mentioned resonant frequencies when talking about stationary waves on a string, but resonance is a broader, really powerful concept, isn't it?
It absolutely is. Resonance is a general phenomenon that occurs when an oscillating system is driven by an external periodic force, and the frequency of that driving force happens to match or be very close to one of the system's own natural frequencies of oscillation. When this frequency matching occurs, energy is transferred from the driving force to the oscillating system very, very efficiently. The result can be a dramatic increase in the amplitude of the system's oscillations, sometimes reaching surprisingly large levels.
One of the most infamous examples always cited is the collapse of the Tacoma Narrows Bridge back in 1940 in the U.S.
Yes, that's the classic, albeit complex, example. While the full explanation involves intricate aerodynamics, specifically aeroelastic flutter, a crucial contributing factor was that the wind blowing across the bridge deck generated forces that caused the bridge to oscillate. Unfortunately, the frequency of these wind-driven oscillations happened to match one of the bridge's natural resonant frequencies for twisting motions. This resonance allowed energy from the wind to pump into the twisting motion, leading to a massive catastrophic increase in the amplitude of the twisting until the bridge structure simply failed and collapsed. It's a stark reminder of the power of resonance.
There are less destructive examples too, right? Like breaking a wine glass with sound.
That's another classic demonstration, yes. Every object, including a wine glass, has natural frequencies at which it prefers to vibrate. If an opera singer, or even just an audio speaker, can produce a sufficiently loud and pure sound tone whose frequency precisely matches one of the resonant frequencies of the glass, the sound waves transfer energy to the glass very efficiently, causing the amplitude of the glass's vibrations to build up. If the amplitude becomes large enough, the stresses in the glass can exceed its breaking point and it shatters. It requires hitting that resonant frequency quite precisely.
And pushing a child on a swing.
That's resonance in action, too. A swing is essentially a pendulum with a natural frequency determined by its length. To get the child swinging higher and higher with minimal effort, you instinctively push them at just the right moment in each cycle. You're matching your pushing frequency to the swing's natural frequency, efficiently transferring energy. Even tuning a radio or an old TV receiver relies on resonance. Inside the receiver is an electronic circuit whose natural frequency can be adjusted by turning the tuning knob. You adjust this frequency until it matches the frequency of the radio waves being broadcast by the station you want to listen to. The circuit then resonates, strongly amplifying the signal from that station while largely ignoring signals at other frequencies.
Okay, resonance is powerful. Earthquakes are another incredibly powerful and often devastating manifestation of wave physics on a truly massive scale.
Yes, earthquakes are caused by the sudden release of stored energy in the Earth's crust, usually due to the movement of tectonic plates. When rocks under stress suddenly fracture or slip along a fault line, this energy radiates outwards in the form of seismic waves. These waves travel through the Earth and along its surface, causing the ground shaking we experience. Seismologists study these waves intensely to understand both earthquakes and the structure of the Earth's interior.
What kinds of waves are actually involved in an earthquake? Are they like sound or light?
There are several types. We broadly classify them into two main groups: body waves, which travel through the Earth's interior, and surface waves, which travel along the Earth's surface, much like ripples on a pond. The body waves include P waves, primary waves, and S waves, secondary waves. P waves are longitudinal waves, just like sound waves. They involve compressions and rarefactions of the rock, with particles moving back and forth in the same direction the wave is traveling. P waves are the fastest seismic waves, and they can travel through solids, liquids, like the Earth's outer core, and gases.
Okay, P for primary, fast, longitudinal. What about S waves?
S waves are secondary waves, and they are transverse waves, like light waves or waves on a string. They involve shearing motions, where rock particles move side to side, perpendicular to the direction the wave is traveling. S waves are slower than P waves. And crucially, S waves can only travel through solid materials. They cannot propagate through liquids or gases because fluids can't support shear forces. This inability of S waves to pass through the Earth's outer core was key evidence that the outer core is liquid.
And the surface waves, you said they cause the most damage.
Generally, yes. Surface waves, which include types like love waves and Rayleigh waves, are generated when the P and S waves reach the Earth's surface. They travel more slowly than body waves, but often have much larger amplitudes and involve complex rolling or side-to-side motions of the ground. It's usually these larger amplitude surface waves that cause the most intense shaking and damage to buildings and infrastructure during a major earthquake.
How do scientists use these different waves to locate an earthquake?
Because the P waves travel faster than the S waves, they arrive first at any seismic monitoring station. The S waves arrive later, and the surface waves arrive last. By measuring the time difference between the arrival of the P waves and the S waves, the SP time interval, seismologists can calculate the distance from the station to the earthquake's origin, called the epicenter. If you have this distance measurement from at least 3 different stations, you can triangulate on a map to pinpoint the exact location of the epicenter.
The magnitude or strength of an earthquake is often described using scales like the Richter scale. Right. How does that relate to the waves?
Yes, the Richter scale, developed by Charles Richter in the 1930s, was one of the first widely used scales to quantify earthquake magnitude. It's based on the maximum amplitude of the seismic waves recorded by a specific type of seismograph at a standard distance from the epicenter. Importantly, the Richter scale is logarithmic. This means that a 1-unit increase on the scale, say from magnitude 5 to magnitude 6, represents a 10-fold increase in the measured wave amplitude. In terms of energy released, each whole number increase corresponds to roughly a 30-fold increase in energy. So a magnitude 7 earthquake releases vastly more energy than a magnitude 5. Nowadays, seismologists often prefer other scales, like the moment magnitude scale, which gives a more reliable measure for very large earthquakes, but the concept of relating magnitude to wave amplitude remains central. These are truly powerful waves carrying immense energy.
Speaking of powerful waves, let's clarify something about tsunamis. They're often mistakenly called tidal waves, but they have nothing to do with tides, do they?
Absolutely not. That's a common misconception. Tsunamis are not related to the daily tides caused by the moon and sun's gravity. The name actually comes from Japanese, meaning harbor wave. Tsunamis are giant ocean waves typically caused by sudden, large-scale disturbances of the ocean floor or massive displacements of water. The most common cause is a large underwater earthquake, especially one that causes vertical displacement of the seabed. Other causes can include major underwater volcanic eruptions, large coastal or underwater landslides, or even meteorite impacts in the ocean. In the deep open ocean, tsunami waves are actually quite different from normal wind-driven waves. They can have incredibly long wavelength, sometimes hundreds of kilometers long from crest to crest. Because they are so long, their amplitude or height in deep water is often surprisingly small, maybe only a meter or even less. You might not even notice one passing if you were on a ship in the deep ocean. However, they travel at extremely high speeds, comparable to a jet airliner, maybe 700, 800 kilometers per hour across entire ocean basins.
So if they're not that high in the deep ocean, why are they so incredibly devastating when they reach land?
Here's where the wave physics comes into play, often with tragic consequences. As a tsunami wave approaches the coast and moves into shallower water, things change dramatically. According to wave theory for water waves, as the water depth decreases, the wave's speed must also decrease significantly. The speed depends on the square root of the depth for these long waves. Also, because the frequency must remain constant, the wavelength must shorten proportionally. However, the wave is still carrying a tremendous amount of energy spread over its vast length. To conserve this energy as a wave slows down and bunches up, wavelength decreases, the amplitude, the height of the wave must increase dramatically. This process is called shoaling. So a wave that might have been only a meter or two high out in the deep ocean can rapidly pile up as it rushes into shallow coastal waters, reaching heights of 10 meters, 20 meters, or sometimes even more, depending on the initial energy and the shape of the coastline and seabed. It's this enormous increase in height combined with the huge volume and momentum of the water surging inland that causes such immense destruction. The 2004 Indian Ocean tsunami provided a horrific demonstration of this devastating power.
That's a sobering reminder of how these principles work on a huge scale. Okay, finally, maybe just a brief word about lasers, another amazing application related to light waves.
Right. LASER is actually an acronym. It stands for Light Amplification by Stimulated Emission of Radiation. That name hints at the core physics principle involved. The key idea behind a laser is getting a large number of atoms or molecules in a special material, the gain medium, into an excited energy state, and then triggering them to emit photons, particles of light, in a very controlled way through a process called stimulated emission.
How does that stimulated emission differ from how a normal light bulb makes light?
In a regular light bulb, like an incandescent one, atoms are heated up and emit light spontaneously and randomly. The emitted photons fly off in all directions, they have a wide range of frequencies, producing white or colored light, and crucially, their waves are completely out of phase with each other. It's incoherent light. A laser works differently. It starts with atoms already in an excited state. When a photon with the right energy comes along and interacts with one of these excited atoms, it can stimulate that atom to drop back down to its lower energy state by emitting a second photon. The crucial thing is that this newly emitted photon is an exact clone of the first one. It has the same frequency, same color, travels in the exact same direction, and its wave is perfectly in phase with the incoming photon's wave. This process can cascade. These two photons can then stimulate two more atoms, producing four identical photons, then 8, 16, and so on. This creates an amplification of light. By placing this gain medium between mirrors, you create an optical resonator that bounces these photons back and forth, further amplifying the process and ensuring the light emerges as a highly directional, intense, and coherent beam, meaning all the waves are in phase.
And the applications that have come from understanding and harnessing that coherent light are just incredibly diverse now.
They really are. It's hard to imagine modern technology without lasers. They're used for high-precision cutting, welding, and engraving in manufacturing. For incredibly accurate surgical procedures like eye surgery, LASIK, and various medical treatments. For scanning barcodes at the supermarket checkout. For transmitting vast amounts of data at high speeds through optical fibers in our communication networks. In CD and DVD players, though less common now. For scientific research in countless fields. The list just goes on and on. They are a perfect testament to how deeply understanding and manipulating the fundamental wave properties of light can lead to truly revolutionary technology.
Wow. We have really covered a vast landscape today, haven't we? It feels like we've journeyed from the very basics right through to some pretty complex and powerful phenomena. We started with the fundamental definition of a wave, that disturbance carrying energy, but not matter. We classified them into mechanical and electromagnetic types. We unpacked their key parameters: amplitude, wavelength, frequency, period, velocity, all linked by that crucial V = lambda equation.
Yeah, and then we looked at how waves behave when they meet things. Bouncing back in reflection, bending due to speed changes in refraction, and spreading out around obstacles through diffraction. And that all-important principle of superposition, how waves simply add up when they overlap.
Which then led us to understand the beautiful patterns of interference, constructive and destructive nadies needing coherent sources to be stable. And the fascinating trapped energy of stationary waves with their nodes and antinodes, and the concept of resonant frequencies on strings and in pipes, plus the pulsing sound of beats when two slightly different frequencies interfere.
And from those general principles, we dove into specifics. The nature of sound with its loudness, pitch, and timbre. The vast electromagnetic spectrum, the unique property of polarization for transverse waves like light.
And we explored the Doppler effect, how relative motion changes perceived frequency, explaining everything from the changing pitch of a siren to using redshift and blueshift to measure the expansion of the universe, and even touching on supersonic travel and shock waves.
Finally, we saw the immense real-world power of these concepts in resonance phenomena like the Tacoma Bridge or breaking glass, the destructive energy carried by seismic waves and earthquakes, the terrifying transformation of tsunamis as they reach shore, and the focused, coherent power harnessed in lasers.
It truly underscores how these fundamental physics concepts provide the essential framework for understanding such an incredibly wide range of phenomena in our physical world. It really feels like grasping these wave principles opens up so many doors to further understanding in physics and beyond.
Absolutely. For anyone studying physics, especially at stages like the AL level, getting a firm handle on wave motion isn't just about passing exams. It's about building a core understanding that will underpin so many other areas you'll encounter, from optics to quantum mechanics to engineering. It's truly foundational knowledge.
So as we wrap up this deep dive, here's maybe a thought for you, the listener, to carry with you today. Next time you hear music, see a reflection in water, feel the rumble of thunder, watch the colors in a soap bubble, or even just observe ripples spreading on a pond, take a moment to appreciate the invisible and sometimes very visible physics of waves at work. These aren't just abstract concepts in a textbook. They're the engine behind so much of what you perceive and interact with every single day. So the question to ponder might be, what other hidden wave phenomena might be shaping your world right now, perhaps undetected? And how might a deeper understanding of these fundamental principles lead you, or someone else, to the next big discovery or technological leap in the future?